Hi everyone! In this video, we are going to focus on the attention layer. We are going to compare different methods that researchers proposed to improve the transformer architecture. In this video, I will make sure to show you the theory behind each method and how to implement it in code. And by the end, we will choose the method that achieves the lowest validation loss. If you forgot about why we use the attention layer in a transformer, let me explain that one more time. Attention is used to help the language model focus on the most relevant pieces of information in the input. In this video, we are going to compare the following methods. We have sparse attention, multi-head attention, grouped query attention, linear, local, and latent attentions. And here you can see that I have tried my best to link to the original papers where these methods have been published. So here, for example, you have sparse attention, and sometimes I link multiple research papers that have talked about that specific method. So if you want to go deeper, please make sure to click on these icons. They are all clickable and they will take you directly to the research paper. Let's start with multi-head attention. This method was introduced in 2017 in the famous Attention is All You Need paper. Again, so here's a screenshot of the first page of that paper. You can click on this image if you want to go directly to this paper in order to read more about it. MHA, which stands for multi-head attention, is the foundational attention mechanism used in that paper. Here is the transformer architecture diagram, and here is the attention layer. You can see that it comes after encoding the input sequence. Here, in that specific attention is all you need paper, we were using positional encoding and word embedding or token embedding to encode the input sequence. And you can see the attention layer comes after the encoding and comes before the feed-forward network. The role of MHA is to compute the attention scores, and it does this independently across multiple heads in parallel. And this is the beauty of this technique, is that we can divide the computation into multiple heads and perform that computation in parallel, which speeds up training a lot. But you might ask, why should we use multiple heads? Can't we just perform a big matrix multiplication instead of dividing that into smaller matrix multiplications? The answer to that question is that when we use multiple heads, the model learns diverse representations because each head focuses on various input aspects. So maybe this head will focus on something, the other head will focus on something else, and this will help the transformer model generalize better. Now, let's zoom into the attention layer. Within each head, the input is projected into three matrices. We have the query matrix, the key matrix, and the value matrix. This diagram contains 6 heads. The first head contains the 3 matrices that I have talked about. And here, before we go to the second point, this arrow indicates that each query vector is compared to all key vectors to measure similarity. Here, when I say query vector, it means that I am taking a slice from that matrix, because the query matrix, it has multiple vectors. So we take one vector from query and we compare it to the other vectors to measure similarity. And here we measure similarity with by using dot product or other methods. This similarity measurements that we are performing gives us the attention score matrix. And here's how it looks like. You can see that this matrix is a square matrix. So basically here you can see that this is a full matrix. So here, this means that we attend from both directions. So if I am at this token, I can look at the tokens that come in the future. For example, if I am here, I can look at the tokens that are before me and the tokens that will come in the future. But the problem is that here we are using a decoder only transformer. We are using that for text generation. This is the task that we are trying to perform. So we shouldn't look at the tokens that come in the future, because the model will cheat. So during training, we should apply a mask to remove the tokens that come in the future. These cells that are colored in white contain zeros. This means that the model will not be able to cheat because it doesn't have that information. And here, the colored cells in this pink color contains the actual attention scores. By using this trick, we will ensure that the model learns how to predict the next token instead of cheating. Okay, so now here is our diagram. I am going to zoom into one head, but the calculation is similar to the other ones. Here is the formula that we use in order to compute the attention scores, and here is the diagram. This is exactly the steps that we are going to follow when we are going to implement multi-head attention in code. Here we have the input. We project that into three matrices: query, key, and value. Let's look at this term inside the softmax function. Here we have q. We multiply that by the transpose of k. So here is k. We transpose it and we multiply that by q. So here, after multiplying these two matrices, we divide by this term just to scale the numbers inside the matrix. I am not showing here, but I'm not showing that division here, just to keep the diagram simpler, but we are going to add this in the code later. After that, we get this matrix, which is basically this term. After that, we apply the masking, as I said, because we don't want to look at the tokens that come in the future. So we multiply this with v, and we get the output, which contains the attention scores. And here you can see that this multiplication is performed on the first head, and we perform the same calculation on the other heads that remain. And at the end, we take the output from each head and we concatenate them to get the full attention scores matrix. In this video, we are going to consider multi-head attention as our baseline. Here are the loss curves for both training and validation. Later in the video, we are going to compare the other methods to this baseline, because multi-head attention is the method that we used in the first course, and now we want to try the other methods to see if they improve the performance of the transformer model. The first method that we are going to compare against multi-head attention is multi-query attention. This method was introduced in the fast transformer decoding paper. Click on the image if you want to read more about that paper. Multi-query attention is a computationally efficient method. Why? Because it reduces the memory usage by shrinking the KV cache. If you are not familiar with this term, KV cache, it means how much memory the key and value matrices take during training or inference. MQA uses one key and one value for all query heads. We have seen this diagram when I was explaining multi-head attention. You can see that in each head we have three matrices: key, query, and value. In MQA, all queries share the same key and value matrices. This means that K and V are calculated only once and then shared between the query matrices or between the heads. This means that the number of parameters will decrease, which might in turn impact the model's performance in some cases. But the major benefit of MQA is the inference speed. This method is way faster than MHA when generating tokens. Let's look at the internals. Same as before. We have our diagram, the attention function, and here is the diagram that shows what goes inside one head. Do you see a difference? The key and value matrices are outside the head. This means that they are calculated once and used inside each head. This is the only difference between MQA and MHA. You can see that the rest is the same. We perform the multiplication, so we compute this term inside the softmax function. We get this matrix, we apply masking, and after that we multiply it by V to get the attention weights. And this calculation is performed similarly on the other heads. It's comparison time. We have the two graphs for training and validation. In both cases, MQA performed better than multi-head attention, which is surprising. The difference is not that big, but it is in favor of MQA. I say that it is surprising because multi-query attention uses the same query and value matrices for all query heads, which means that we will have less diversity when training this model. But in this dataset that I am using, it seems that MQA worked better than MHA. But again, the difference is not that big. I have also mentioned that MQA is faster in inference than MHA, and here is the diagram that I have tried to create in order to illustrate this. You can see that here we have in the x-axis the number of tokens to generate. So I have tried to generate 100 tokens up to 2000 tokens for MHA and MQA. And here on the y-axis, we have the inference speed or the inference time in seconds. You can see that MQA is 7 times faster than MHA when generating 100 to 200 tokens. But after increasing the number of tokens to generate, that benefit starts to shrink. You can see that here at this point, MQA becomes 6 times faster than MHA. Here it starts to decrease again, so it's 1.7, and when we reach 2000, it became worse, so it's 0.8 times worse or slower than MHA. In the fast transformer decoding paper, where Noam, this researcher who worked on MQA, showed that this method was 12 times faster than MHA with a sequence length equal to 128 tokens. So this matches what we see. I mean, there he was using a very powerful hardware, and here I have just an RTX 4070, which is not that impressive, but still you can see that here. So he used 128, here I have 100 tokens, and here I got 7 times faster inference speed. And this, again, the model here is small, so if I increase the model size, this value will have changed also. So but this matches what Noam observed when he was writing that research paper. And here it's surprising that MQA becomes bad when we increase the number of tokens to generate. Maybe my implementation is not optimized, but since Noam didn't try to compare the inference speed at higher number of tokens to generate, I can't say 100% if this method works only when we generate fewer tokens, and it works bad when we try to generate large sequences of text. Now we have compared the performance of MQA to MHA. Now let's see how to implement this in code. I am in VS Code, and here I have opened the diagram. This is exactly what I have showed you in the slides. Let's put it here because it will help us see what we are doing inside this script. I will make it smaller. Open model multi-query attention, and like the previous video, everything will stay the same, but we are going to change just what we are concerned with. And here we are going to change the attention layer. So here I have created this multi-query attention class, and inside it, in the constructor, we have the number of heads, the head size, and here are the matrices. So we have the key matrix, value, and query. Okay, and we have the rest of things. We'll come back to the rest. Okay, so in the forward pass, now I will zoom in. We get the batch size, the sequence length, and the embedding size from the input. Here we compute the key and value matrices, and after that we get the query. So here everything is the same, but I have said that K and V are shared between all query heads. So after getting the query, you can see that here is the shape. So it's going to be batch size by sequence length by number of heads times head size. So we are going to reshape this to add the number of heads dimension. So here we have batch by number of heads by sequence length by head size. So you can see that here this represents all query heads, but remember that we have only one key and value head. We are going to also reshape K and V in order to add this dimension, but we are going to put 1 because this is what I said. In multi-query attention, we have just one key and one value, and those are going to be shared by the query heads. We are going to use broadcasting to multiply K and V so that we can multiply them by Q. So let's see how to do this. So this is the only thing that we need to do. So here, when we are going to compute the multiplication between query and the key, Python will use broadcasting to make sure that the shapes match. So here, when we perform this operation, you can see that we cannot do it because here we have B times number of heads, and here we have B times 1. Python will try to match these two dimensions by multiplying the key number of heads times. So here we will have B times number of heads. And this is why I said that repeat for each head. Okay, and the rest will stay the same. So here we multiply Q and K, we divide by the head size. So this is the scaling factor. After that, we are going to, so here, let me zoom in again. We are going to perform the masking. We are going to use the softmax function, apply dropout, and at the end, multiply the masked weights matrix with V. So V, we are getting it from here. And again, you can see that here are the shapes. So attention weights is B times number of heads times T, but V is B times 1. So these two dimensions do not match. But luckily, Python will use broadcasting to solve this issue for us. So it will just keep duplicating V number of heads times so that this matrix multiplication can be computed. And at the end, this is the shape that we are going to get. Here you can see that we have tried to merge all heads into one simple class instead of dividing this into multiple heads and then concatenating the results of each head. By the end of this forward pass, we have everything concatenated. So you can see that here we transpose the first and second dimensions so that we can basically merge the number of heads by head size into one dimension, which is the number of channels. And after that, we are going to return the output, which contains the attention weights. This is exactly what we need to change, just the attention layer. The rest will stay the same, okay? And like before, like in the previous video, I have created a notebook to try this. So it's this one, improving transformer multi-query attention. And here, all I did is that I imported the GPT language model class from this new script that I have created. And yeah, the rest is the same. So here we divide the data into training and validation. And then I run this. And at the end, I make sure to save the training and validation losses so that I can print the curves and show them in the slides. Now let's go back to the slides in order to explain the next method. Local attention is the next method that we are going to focus on. It was mentioned in these two papers. Here they are. Again, you can click on them if you want to go deeper. Local attention works by limiting the attention span of each token to a fixed size window. Here is the full attention scores matrix, and this is how it looks after applying a window size of 3. You can see that in this case, a token can attend up to 2 positions in the past. If I am, for example, here, I can only look at the 2 previous tokens, but you can play with this value. This makes local attention efficient, but it's a bit tricky to get the most out of it. You need to do a lot of optimizations to benefit from this approach. The problem with limiting the attention span to a fixed window is that long-range dependencies are not captured because the model is focusing on the local context only. Also, this method, like MQA, multi-query attention, might lead to a degradation in the performance of the model. Let's see what happens inside one head. We have our formula and here is the diagram. It is similar to the previous ones. The only difference is here. You can see that when we apply the masking, we make sure that we also apply the window so that we also turn the other values here in this lower triangle to 0. So we will have 0 here, and the values in the middle will have the attention scores. And finally, we multiply this masked attention weights with the V matrix in order to get the output. Now let's compare local attention to the previous methods, multi-head attention and multi-query attention. Here are the two figures. And as you can see, local attention is beating the other two methods in both training and validation. So you can see that the difference between local attention and multi-query attention is minimal. But if we compare local attention to the baseline, which is in this case, the standard multi-head attention, you can see that the gap is starting to increase. Here is the inference speed. You can see that local attention is not as fast as multi-query attention. So you can see it's even worse than multi-head attention in this configuration that I have tested. We also have other variants of this method. So here we have dilated slide-in window. This is how it looks like. We also have chunked slide-in window. This is how it looks like. We can also combine between the two. So we have global plus slide-in window. Here is how it looks like. So we still have the slide-in window, which is what I showed you earlier, but we add these global, you add these for the tokens that should be, that should attend to all the tokens. For example, the special tokens, like the start of text, end of text, etc. Okay, now we have seen the results. Now let's see how to implement this in code. Here is the new script that I have created. And here is the diagram that explains how local attention works. Here we have the three matrices, key, query, and value. Here they are just linear layers, but we are going to use them in the forward pass. Okay, so let's start. First, we have the input X. We are going to project it into the key and query matrices. So here we are using the key and query linear layers, and the shape will be batch size by sequence length by head size. This time I have the head class, but like the previous method, which was multi-query attention, we can combine them inside the attention class. It's up to you to decide, but it's similar. When you add the head class, at the end you will need to concatenate the results. But if you want to remove the head class, you will do everything. So instead of having 3 dimensions, you will have 4 dimensions. The first one will be batch size and the second one will be the number of heads. Okay, so now we get these two matrices. We are going to apply our formula. By now you should know it by heart. Now we are here. We have the full attention weights that we got here. Now we need to apply this slide-in window masking. So how do we do this? Like what I did in the previous video. If you don't understand how this is implemented, the easiest way is to open the terminal. Let me activate the environment, and here open a new Python session and start experimenting with this. So for example, here, if you don't understand, okay, let me remove this because I don't have enough space. So if you don't understand, for example, what is happening here, how are we generating this matrix, you can come here. For example, here I need to import PyTorch. And here, try to create small examples. For example, let's set T to 4. And here I need, so I will just take this. I will not take the device. Let's take unsqueeze. Okay, let's look at row indices. Okay, so here we have 4 rows and 1 column, and column indices should be similar, but instead we will have 4 columns and 1 row. Column indices. Let's look at column indices. Okay, so as you can see, we have 1 row and 4 columns. Okay, so why did we create these two tensors? Well, here is the first step. We are going to prevent the attention to future tokens. Okay, so how do we do this? If I take this and again look at causal mask, as you can see here, false means 0 and true means 1. So we can see that by doing this, we were able to remove the upper triangle from the so this is the mask. We are going to multiply this with our attention weights matrix in order to remove the upper triangle. And how did we do this? You can see that here we have 4 rows and 1 column. Here we have 1 column and 4 rows. And this is the beauty of Python. So Python under the hood will use broadcasting in order to duplicate one of these tensors so that we can perform this operation. And this, because here we have 4 by 1 and here 1 by 4, this will be multiplied 4 times so that we get a 4 by 4 matrix. If you don't do this, you will never, it's going to be hard for you to understand this just by imagining it. You need to open the terminal, open a Python session, and tinker with these values or with these expressions that are in the forward pass. This is how you understand any model. Okay, so that was the first step. This is what we have done before, but now we need to apply that sliding window. So here we have this parameter. In this case, because we have a small matrix, I will make sure to have a small window size. Let's set it to 2. And here, let's see the second step. So here we are going to create the local window mask. So this restricts the attention to a local window around the current token. Okay, this is what we have said. And this is the formula that we need to apply. So let's just take it. Here, make sure to not take self. And here, I need to add 1. Now let's look at local mask. And as you can see, we have everything is set to true. So the upper triangle is set to true, but the lower triangle is set to false. So this is the inverse of what we had before. Now we just need to combine the two. And we are going to use the AND operator so that we multiply the two values. So true times false will give us false. True times true, or true and true, will give us true. So let's look at the final mask. And as you can see, here is the upper triangle. It is set to false. This is exactly what we used to do before, but now we applied the local attention mask. And as you can see, we have 2 values max in each row. So this means that it works. And after that, we just need to apply this mask to the attention weights. And finally, after that, we use the softmax function. And at the end, we multiply the weights with the V matrix. After that, we get the output. And remember, this is just one head. So now we need to go. So this was already done, but I just wanted to show you this. So here are the full list of heads. Here in the forward pass, in the attention class, we are getting the output for each head independently, but we need to concatenate them. So as you can see, the shape at the end will be batch size times time sequence or the sequence length times the number of heads times head size. This is how it works, and the rest is the same. Now I have also created another notebook where I have used this class, and this is how I was able to show you the comparison between local attention and the other methods. I hope that you understood this method. Now let's move to the next one. Grouped query attention is our next method. This one was mentioned in this paper. Training generalized multi-query transformer models from multi-head checkpoints. Click on the image if you want to read more about this paper. Grouped query attention is the generalization of multi-head attention and multi-query attention. This is the diagram for multi-head attention, and here is how it looks like for GQA. In grouped query attention, we try to form groups In this example, we have 6 query heads, and we have created 2 groups. And in each group, the query heads share the same key and value. In multi-head attention, the number of groups is equal to the number of heads, which means that each head contains 3 matrices, key, query, and value. In multi-query attention, the number of groups is equal to 1 because all queries share the same key and value. But in GQA, we have the flexibility to change that value instead of being 1 or the number of heads. This means that grouped query attention offers an ideal trade-off between speed and performance. It falls between multi-head attention and multi-query attention. It is fast and also gives good results. When setting the number of groups to a value lower than the number of heads, GQA reduces the number of trainable parameters compared to multi-head attention. Let's zoom at the attention layer to see what happens exactly. This is how the diagram looks like for GQA. I want you to focus on this part. Here we are inside the attention layer. Remember that each group shares one key and value matrices. This means that we need to duplicate the K and V matrices multiple times to match the number of queries in one group. Let's take this as an example. You can see that in one group we have 3 queries, but we only have one key and one value. So if you try to multiply these 2 matrices together, you will get an error because the shapes do not match. And I tried to depict that with this change. So here you can see that query is bigger than V in size. So here we need to duplicate V and Q multiple times so that we have the same size. And after that, we can apply this formula. So here, after duplicating K, you are going to transpose it, multiply it by Q, and then apply the mask, and after that, multiply everything by V in order to get the output. But this is the important thing to consider when trying to implement this in code. Are you ready to see the comparison? Here you go. The model under grouped query attention has destroyed the previous methods. Look at the gap between the loss curves. It's huge. This method performed really well on both training and validation. And here, I want to put a big asterisk on this result that I got. I have used a specific dataset for the Moroccan Darija. And maybe because here I took 1000 batches in both training and validation to basically draw these curves. Maybe I would have got different results if I have increased that value from, let's say, 1000 batches to 2000 or 10,000 batches. Maybe these curves will have changed, but here I am just showing you how to implement these methods, how do they work under the hood, and after that, if we change the dataset, we might get different results. Maybe I will try to rerun the grouped query attention another time just to verify that this result is consistent and update the graphs if I see something has changed. But here, as I said, the curves, each one will get different curves, each one will get different loss values depending on the model size and the data that you have used. Let's also check the inference speed. Here is the diagram. GQA is fast like multi-query attention, but it's a little bit slower than it. You can see that MQA is in orange. So yeah, the difference is not that big, but it's slower. Because here in multi-query attention, we have one group, but here we have more than one group. So we have more parameters than MQA. That's why it's a little bit slower. Now let's go to VS Code to see how to implement this. I have created this script, model grouped query attention, to implement this technique. Here we have the grouped query attention class, and let's see how it works. Here we have the classic parameters, number of embedding, number of heads, etc. But I also added the number of key value heads. Basically, this is the number of groups. So here I have this comment because, as I said, GQA is a generalization of both MHA and MQA. And here, if number of KV heads is not specified, we are going to set it to the number of heads to fall to MHA. But yeah, we shouldn't do that. We should specify a value greater than 1. And here, if number of KV heads is equal to 1, that means that we are going to use MQA. Otherwise, it's GQA. So number of KV heads should be greater than 1 and less than number of heads. So after that, so we are storing it here. We get the head size and the number of queries per KV head. We saw that in the slides. We had 2 groups, and in each group we have 3 queries, and this value stores that information. I will go directly to the forward pass so that we follow the diagram that we have here on the right. So from the input X, we project it to get the query, and here is the shape. So we have batch size, sequence length, and number of embedding. After that, we are reshaping the query to have this shape: batch by number of query heads, by sequence length, by head size. And here is how we do that. It's simple. We get those values that we got from the constructor and apply the transformation. After that, we get the key and values. And here, remember, so V and key are small because in each group, all the queries share the same key and value matrices. So we get the key matrix like this. We have this key matrix that we have defined here. It's a linear layer, and the shape will be like this: batch size, sequence length, and here the last dimension is number of KV heads times the head size. And remember, number of KV heads is the number of groups. So here we will have 2 keys. So here I am referring to the example that we have seen in the slides. So query, we will have 6 query heads, and here we will have 2 key heads. And because the number of groups is set to 2. So we are going to reshape this again to separate the head size from the number of KV heads. And we are going to do the same thing for V because they are similar. So again, V is, we are going to use the value matrix to project X to get the V matrix. And after that, we are going to reshape that tensor. And now this is the part that I have highlighted in the slides. So from here, we need to duplicate V multiple times so that we match the number of queries that we have. In that example, we have 6 queries and 2 values because we have 2 groups. So we need to multiply V and Q 3 times. So we are going to multiply 2 by 3 to get 6 value heads and 6 query heads. And this is the role of repeat KV. So this function that I have defined, I will show you what it does. We'll take one of these matrices, so K or V, and it will multiply it number of queries per KV times. And number queries per KV is equal to 3. So 2 times 3 will give us 6, and this will match the number of queries. Okay, so let's go inside repeat KV to see what is happening. We have the tensor and the repetition times. How many times do we want to repeat that tensor? So if repetition times is equal to 1, we are going to return that tensor. There is nothing we need to do. But if this is greater than 1, we have this lovely function that PyTorch provides us. It's called the repeat interleave. And this will take, so you take the tensor, you call that method, and you tell it how many times you want to repeat it. And here we are specifying the dimensions that we want to repeat. Okay, so here we have number of KV heads, and this is what we want to repeat because number of KV heads is equal to 2 because we have 2 groups, but we want to multiply that to get 6 at the end. After that, this should be the number of query heads. This is why we targeted this dimension specifically, because we wanted to go from 2 to 6 to the total number of queries that we have. So this is a really great function that simplifies things. If we didn't have it, we had to do a lot of gymnastics to get this output. So yeah, this is what we have inside the repeat KV, and we use it for both key and value matrices. So yeah, now everything is prepared. The rest is the same. So we apply the attention formula, we get the weights, we apply the mask, softmax, we add a little bit of dropout. We multiply the masked matrix with V to get the final output, which in this case is Y. But remember, since we have 4 dimensions, we need to merge the number of query heads and head size. And this is exactly what we are doing here in these lines. And finally, we apply another dropout and get the final output from this grouped query attention class. And again, here you see that we didn't use the head class, so we have merged everything into the attention class. And as you can see, sometimes I show you how to use the head, so if you want to perform the calculations separately, you can do that. And sometimes I show you how to merge the head inside the grouped attention into the attention layer. And whenever you fuse the head, you always add another dimension. When we don't have the head class, we will have 4 dimensions. But if we decide to add the head class, we will have 3 dimensions. And at the end, you concatenate the output from each head separately. And again, after I have created this, I have made sure to create a notebook that I have run in order to get those results. And you can find it here. So let me search for it. It's this one, 923, improving transformer grouped query attention. Now let's go back to the slides to learn about the next method. Linear attention is the method that we are going to focus on now. Read the following papers if you want to understand this method deeply. Again, you can click on the images if you want to get a direct link to the papers. We know that multi-head attention scales badly with long sequences of text because of the ON squared complexity. Linear attention tries to solve this issue by using less memory in order to be efficient. How does it do that? Well, researchers found a way to approximate the attention formula with this one. You can find this approximate equation in the paper that I have highlighted in the previous slide. And as you can see, here is the equation number 5 is exactly what I have written here. Also, researchers found that even though we are doing this approximation, which goes from big O n squared to ON, basically turning the complexity to be linear, they found that this method can give you good performance even with this approximation. Now let's see how the attention layer looks like. First, we have our linear attention formula, and here is our diagram. This time, the diagram is different than the previous ones. First, we have this phi function that we apply to the query and key matrices. This gives us phi q and phi k. Also, if you look at the formula, we can turn it into this. So Si is basically this summation and Zi is this summation. So we can also compute these terms. So we have already computed phi q, it's this one. Now we can compute Si. So Si is basically phi k times the transpose of V. So we are going to take phi k, here it is, and we are going to take V. Here I didn't show V transpose, but we should transpose it before multiplying it by phi k. This gives us Si. And Zi is basically phi q, phi k. So Zi is phi k. Now we need to multiply Si with the transpose of phi q. Here it is. So Si times phi q transpose. And here basically we need to multiply Zi with the transpose of phi q. And here it is. So Zi multiplied by phi q transpose. And after that, we divide the numerator with the denominator with this operator. And at the end, we get the output, which gives us the attention weights. You will see that this diagram will help us understand how to implement this in code. It will be a direct translation from these steps that you see here into code. Now let's compare linear attention with the previous methods. Here is the graph for the training loss and the graph for the validation loss. Because these curves are close to each other, let me zoom in a little bit so that we can see clearly. linear attention is this pink curve, and overall it's comparable to multi-head attention. So you can see here in validation, both MHA and linear attention are very close to each other. So even though it is comparable, it's not the best method in our benchmarking. But you can see that we have a method that works very fast and gives us the same performance as multi-head attention. Let's see the inference speed to verify if this is correct. So linear attention is this green bar, or this light green bar. You can see here, let's go to 2000 because here where we see the big difference. You can see that linear attention is super fast, and that's because it doesn't use a lot of memory. I have an RTX 4070 and I have 8 gigabytes of VRAM, and MHI was using almost 7 gigabytes while linear attention was using only 3. This is why this method is super fast. Now let me open VS Code in order to show you how to implement this in code. Here is the script that I have created. It's called model linear attention. We have the linear attention class, and as always, let's go directly to the forward method because here we have the implementation. So first, what do? We project the input text into the 3 matrices. This is what we are doing in the first step. And here you can see that we have the phi function. Let me zoom in. Okay, that's better. Phi is defined like this. It's ilu plus 1. If you are wondering what is this function, basically it's an activation function. We have sigmoid, tanh, relu, etc. And ilu is one of them. So this was the activation function that the researchers have used in the research paper. So we are using that also. But if you want, you can change this and use other activation function. Now let's continue. We have the projections. Now we need to reshape because again, here we are fusing the head into the linear or into the attention layer. So we need to have 4 dimensions instead of just 3. So we are introducing the number of heads at dimension. As you can see, this should be the final output. Batch size by number of heads, by sequence length, by head size. We have the projection, we have reshaped them. Now we need to apply the phi function to the query and the keys. And this is what we are doing here. So we take the query, we take the key, and we apply the feature map. This gives us phi q and phi k. Okay, so now we need to compute si and zi. So here is S cumulative. S cumulative is basically si. And if you, si is what? Is the multiplication of phi k with v. So here is phi k and here is v. And here we are introducing new dimensions so that we can multiply these 2 matrices. So here at the end it should give us, so here head size by 1, 1 by head size. So at the end it should be b by number of heads by t by head size by head size. And zi is just phi k. So there is no multiplication needed here. Okay, now we need to compute the numerator. So the numerator is basically si times phi q transpose. So here is phi q and here is si. That gives us the numerator. And here I try to also show you the formulas so that you don't get lost. Now the denominator is zi times phi q transpose. So here is z and here is phi q. And we also add an epsilon. Epsilon is a small value. I think here it is set to, let's see, it's set to 10 to the minus 6. We are adding the epsilon because this is the denominator. Let's say that this term was equal to 0. We shouldn't divide by 0 because that would give us infinity. So we add that small value to prevent that from happening. And at the end, we get the attention weights, which is the numerator, which we get from here. We divide it by the denominator. And finally, because we have 4 dimensions, we need to fuse those into just 3 so that we get batch size by sequence length by the number of heads times the head size. And finally, we apply the projection and dropout to the output so that we get the dimension that we are looking for. Okay, so this is how you implement linear attention. And if you are wondering, I also have created a notebook to run it. It's 924 Improving Transformer Linear Attention. Now let's go to the slides to learn about the next method. Now let's talk about a paper called Big Bird, which introduced sparse attention. Click on the image if you want to read more about the paper. Big Bird is designed to process large sequences of text without sacrificing the performance. Big Bird uses sparse attention, which is designed to reduce the computational and memory complexity to be linear. We call this big O of n. Sparse attention is the sum of global attention, which looks like this, random attention, and the sliding window attention, which we also call local attention. This gives us Big Bird, which is sparse attention. We have seen that when we used local attention, we were capturing only local dependencies. But Big Bird, because it uses this mix of attentions, let's call it like that, it captures both global and local dependencies. Let's zoom into one head to understand how to implement sparse attention. You can see that the diagram is big, but it's simple. Let's start by computing the weight matrix as we did before. First, we take the input, we project it into the three matrices, and then we compute what we have inside the softmax function. That will give us the raw weights. And now this is the change. So we need to create a mask in order to multiply it with the weights matrix. And this is what we do. Here we have the local attention mask. You can see that here we have zeros in the upper triangle and the lower triangle. We have global attention, which looks like this. And finally, the random attention mask. Here, this symbol means OR. So we are going to take these masks. You can see that the values that are colored in blue, or the cells that are colored in blue, contain the number 1 or true, and outside that we have false. When we use the OR operation, we are going to fuse these three masks into one mask. And as you can see, this gives us what we have seen in the previous slide, which is the sparse attention. And you can see that here we have a mix of global, local, and random masks. And here we also create the causal mask because we want to remove the future tokens from the mask. And here we use the AND operation. So AND, it's simple. If you have true and true, that gives you true. If you have true and false, that gives you false. By using this operator, we get this final mask. And now we take the final mask, we multiply it with the weights matrix. That gives us the masked tensor that we can then multiply with V in order to get the attention weights. Now let's compare sparse attention to the previous methods. Here are the two graphs. Again, because the curves are close to each other, I'm going to zoom a little bit. Big Bird is this light blue color. And as you can see, it performed good. The performance of sparse attention is good. So it's close to local attention in both training and validation. Now let's see the inference speed. But the problem is that Big Bird is slow because here we are combining multiple attention mechanisms and that slows down this approach. I mean, we can play with the hyperparameters in order to, for example, you can play with how many random cells you want to add, the size of the window, but overall, when you add all those attention mechanisms, you will get a slower solution. And because here, if I go back, here we do a lot of multiplications. So we have a lot of matrices that we need to compute before getting the final attention weights. That also makes the approach slower. It doesn't use a lot of memory, which is good, but maybe the implementation needs to be optimized. Now, let me go back to VS Code in order to show you how to implement this method. I have created this script, which is called model Big Bird, and we have the head class. So let's go directly to the forward pass and let's see what we have. So first of all, we compute the query and key matrices. Then we multiply them together in order to get the weights matrix. And now we stop. So we go down. Let me zoom in. And things might seem familiar to you because we have seen this before. In order to create this mask, we create two vectors or two tensors, row indices and column indices. We use this operation in order to get the causal mask, which is this one. After that, we are going to compute the local window mask. We get it after performing these operations. And this is exactly what we have done in the part where I have talked about local attention. After that, we have global mask. And here we need to specify the number of global tokens. Because as you can see here, for example, we chose just one token, but we could choose multiple tokens. And after that, we have random attention that will give us this mask. And then, so we get here the random columns. Now we combine the local, global, and random. So here I forgot to add and random components. Okay, so you can see I am using the OR operator in order to combine those. And finally, when those are combined, I am using the AND operator to multiply the causal mask with the final mask. That gives me this, which is this value, this variable, final mask. Now I apply that to the weights matrix, and then I multiply that with V in order to get the output. I went very quickly. As I showed you before, you should not get scared if you see a lot of code. If you do not understand, always open the terminal. Let me activate the environment, open a new Python session and start playing with this. You should not get scared if you see a lot of code. For example, okay, so I am here. Let's create, or let's import torch at the beginning. Now let's create small examples. There is no need to have big matrices. So small examples always help you understand the concept. So for example, here I am creating a random input tensor. Here the batch size is set to 1, the sequence length is 6, and the embedding dimension is 16. And now you can come here, for example, take this, paste it here, look at B, okay, that's 1, etc. And you can verify. So after that, I can come here, take this. So I need number of embedding. Let's set it to 16. Let's set the head size to be 8 so that I get two heads. And now I need to import an n. Let's get the key. Okay, now I can go back and use this. So now I can create the key matrix or the key tensor, give it x, and that gives me the K matrix, and I can look at the shape. Okay, so that makes sense. So K and Q are of shape B times T times head size, and this is what I get. So this is the batch size, this is the sequence length, and this is the head size, and this is exactly what I have just set here. So head size is equal to 8. You can verify these just like that. It's hard to visualize these things in your head because there is a lot of code. And especially if you work with large matrices, that becomes very, very unintuitive. But choosing small examples will help you understand everything. Okay, so now you can do the same thing. Let me continue just a little bit. So again, I can go back. Since key and query are the same, I can remove this, replace that with query. I can get the query like this. And again, I can look at the shape, and that gives me the same result. Now I can go down and compute the weights. So let's take this, paste it here. Let's look at weights. Let's get the shape. And this gives me 1 by 6 by 6, which is exactly what I have mentioned in the comments. So batch size by T by T. Now I can, for example, take this. I just want to show you the masks really quickly. Okay, so I don't need to have a device, but let me just set it to be CPU. Now let's go back. Let's do the same for columns. Okay, and now let's get the causal mask. I know we have seen these things, but I just wanted to show you how to visualize everything. So you can see that the upper triangle is set to zeros, which is what we want. This is exactly the definition of a causal mask. And again, if I come here, let me set the window size to be 2, and let's take these conditions. Okay, here is the first one, here is the second one, and let's get the local attention mask. Now let's look at it, attention mask, and voila, as you can see, the upper triangle and the lower triangles of this tensor are set to 0. But here we have 2 values in each row that are set to true. So this is the local mask. And here we also, if you want to create the global mask, as I told you, we need to set a number of global tokens. Let's set it to 2 because the matrix is small. So I can take this, put it here. I can do this for both query and key. And let's look at global attention mask. You might find this strange because we don't have a square matrix, but because here Python will always remember that Python uses broadcasting. So here you have 6 by 1. After that it will become 6 by 6, and everything will work. And also we can do the same thing here for random attention mask. So I have the value now. Okay, so here we have just created a matrix of zeros, but after that we are going to again specify the number of random tokens that we want to have. Let's set it to 4. Okay, so this gives me random columns. So this just will tell me where should I put those. Here I have the row selector. Sorry, I'll just go through this very quickly just to show you the final output. And as you can see here, for example, we have true in some other places, but as you can see, it's random. And now I can combine the 2 or combine the 3. So I can take this and put it here, combined mask. Just a small trick, if you find it very difficult to see the trues and falses, you can use the .int method to convert that into integer. So as you can see, so this is the combined mask. So we have the global mask and we have some random values also. Let's do the same thing for random just to be able to see that. And as you can see, so everything is random. What you should take from this is that never get discouraged. You have the code in front of you. It's easy to use small examples in order to understand how things work and how the matrices looks like. And this is exactly why I add these graphics, just to show you how things are implemented, because you can easily find these steps in the code. So you can see that here the OR operation, for example, it's here. So you can easily find the step in the code, and everything should be familiar to you. And this will help you visualize the attention layer very easily. Okay, so after getting the output, as I said, because we are using the head, we need to go to the attention class, and here we need to concatenate the output of each individual head. And again, I have created, let's see, so where is it? 925, improving transformer big bird attention. This notebook, I have used it in order to import the GPT language model class from this script and in order to run the experiments. We are near the end of this video. We have one last attention method to look at, which is multi-head latent attention. So let's go back to the slides in order to understand how that one works. This is the final attention that we are going to look at. It is called multi-head latent attention, and it was introduced in the DeepSeek V2 paper. I highly recommend reading this paper because they have explained how they created this method or this attention mechanism in detail. They have showed all the mathematical equations, and even they have a graph that explains how it works under the hood. Click on the image if you want to read more about it. MLA is an efficient method that compresses the KV cache. We have talked about KV caching before. It means that you are going to store the key and value matrices, and this becomes a bottleneck, especially during inference, because if you are generating large sequences of text, you will need a lot of memory in order to store those matrices. So DeepSeek, with this method, they have showed that they can reduce this KV cache by compressing it. And the great thing about this is that it does not sacrifice the performance, and it guarantees faster inference. We have seen that methods like multi-query attention or grouped query attention also tries to lower the KV cache, but the problem is that the performance might degrade. But here with MLA, it guarantees both things. MLA incorporates latent representations into the attention mechanism. We are going to see this in the implementation. Instead of directly projecting the input X into the tree matrices, we are going to project that into a latent representation, and from that latent representation, or we can also call it latent embeddings, we are going to generate our key, query, and value matrices. MLA is very fast compared to MHA. We are going to look at this in the inference speed test. Now let's see how this method is implemented. I want you to focus on these two matrices. So here, as I told you, instead of projecting X into the three matrices, key, query, and value, we are going to have an intermediary step. This is called compressed query, and this one is compressed key and values. From these latent representations, we are going to get the query, key, and value. And after that, the rest will stay the same. But this is the thing that was added, and this is shared by every head. And this helps reduce the KV caching, because you only need to cache these two matrices, and later you can generate the rest, because from from CQ we get Q, and from CKV we get K and V. Now let's compare the results. Again, we have the graphs for training and validation, and here multi-head latent attention is this curve. You can see that here in validation, it is very close to local attention. Again, take these results with a grain of salt, because we might get different results if we decide to change the hyperparameters or how many batches we include in the testing. And as you can see, we get results better than MHA, even though we reduced the KV caching. Now let's see the inference speed, because this is very interesting. So MLA is colored in black, and as you can see, so let's go to 2000 tokens, because this is where the other methods struggled. And as you can see, MLA, as I told you, is really, really fast. So we can generate a lot of tokens without sacrificing the performance. And here, the one that was very close to it, it's linear attention, because linear attention is also good, because as we have seen, it reduced the complexity to ON instead of ON squared, but MLA is the best. Now, let's go to VS Code in order to see how to implement this. I have created this script, model multi-head latent attention, and everything is implemented in this DeepSeek MLA attention. As I told you, I have been inspired by the research paper that they have published. There they have shared everything, so that was a great resource. And let me zoom in here, because we will need this diagram. Okay, let's get started. And here also I want to mention that these terms that we see here are basically the terms that they used in the research paper. Let me open that research paper so that you can see these things with your eyes. Here is the research paper, and here you can read the abstract and the introduction, and also the architecture chapters, because here they explained multi-head latent attention, and they have a good diagram that helps you understand how it's implemented. But I want to go to the appendix, because they have gathered all the formulas here. Okay, so now let me zoom in a little bit. And as you can see, here are the terms that I was talking about. So these matrices that you see here, for example, WDQ, WUQ, etc., are here. So you can see here is the WDQ, WUQ, etc. And the terms such as CQ and where is the other one? So you can see CQ and CQV. Here it is CQV. These are the terms that I have showed in the diagram. Okay, so let's continue. I just wanted to show you this because this is a little bit different from the other scripts that I have created. I try to make sure to use descriptive names, but since I was inspired by the research paper, I try to stick to it as much as possible. Now let's go to the forward method. Again, we extract the batch size, sequence length, and embedding from the input. Now let's start. So here we need to get CQ. So here I called it compressed Q latent, and we get that from the WDQ. And WDQ means we are down projecting. And after that, we apply layer norm. This is what they have applied in the research paper. And after that, after getting CQ, we are going to project that back to UQ. We are going to project that to get the Q matrix. And here, if I go back to WUQ, you will see something interesting. We go from number of embedding to this compressed dimension, and WUQ, which is here I called up projection, will get back from Q compression dimension back to the number of embedding. So basically here we are making the matrix small, and after that we go back to the big matrix. And this is why this method is fast, because here we have a small matrix that compresses the knowledge into a small space. Okay, so these are the two matrices that we have used in the first place, in the first step. And after using WQ, we get the Q matrix. Here I called it Q final. And we do the same for CKV. So we use this matrix. D means down and U means up. So we are going, again, if I inspect WDKV, you will see that we go from number of embedding to another small space. Okay, so that gives us CKV, which is this. And from CKV, we need to get the key and value matrices. This is exactly what we are doing here. After applying layer normalization, we use WU key and WUV in order to get those two matrices. And if you have noticed, we don't have the head class. So we need to introduce the number of heads dimension. We get Q final. We try to extract the number of heads from the C channel or from the C dimension. I think you should be familiar with this. We have done this multiple times. I want to show you something new that I haven't used in the previous scripts, is this function scaled.productAttention. PyTorch provides this method that calculates the attention scores. So I just wanted to show you this because previously we were doing this manually. You can see that it handles softmax, scaling, and causal masking. So there is no need to do that manually. You need to give it the query, key, and value matrices. If you want to give it a custom mask, you can do that. But because here we are setting is causal to true, that will be handled by PyTorch. But if you want to provide another mask, just set it here. And here we are providing the dropout probability. After that, we need to concatenate these two dimensions in order to get just one. So we are going to get the C channel again, or the C dimension. Here we have this WO, which basically will give us the output. So we are going to project the attention weights into another matrix that we call output, which is basically this one, and we are going to return it. So let me close this file because I don't need it. And I have also made sure to create a notebook. So it's called 926, Improving Transformer Multi-Head Latent Attention. So here I have imported the GPT language model class from this script, and everything stayed the same. We have reached the end of this video. I really hope that you have enjoyed it. Before I finish this video, I want to show you basically what we have. The baseline was standard multi-head attention. We have used many attention mechanisms. We have compared them to the standard multi-head attention, and we have seen that all of them performed really well compared to standard multi-head attention. Here you can see that I have picked multi-head latent attention and grouped query attention for two reasons. We have seen that multi-head latent attention was super fast compared to the other methods, and it used less memory overall. And grouped query attention, you can see that here the gap is very huge, and this is on the validation set. But it was slower compared to multi-head attention. And here, I think that for some reason, grouped query attention worked really well because I have maybe used a small number of batches in the evaluation. As I said, I took 1,000 batches from the training set and the validation set as an evaluation set. Maybe if I increase that to, let's say, 5,000 or more, maybe this graph would have changed. But for some reason, maybe grouped query attention got lucky and we got this huge difference. But I think I will stick with multi-head latent attention because it's fast and it performed well. That's it for this video. See you in the next one.